Welcome everyone to another little big lecture. Today we're going to talk about a topic I've been meaning to discuss for a while now. This is a cool one, an epic one in the history of science. We're going all the way back to 1905 with Einstein's 1905 papers that he distributed in a physics journal. Did our boy Albert Einstein. He did this in 1905. This year is known as the Annus, I have over here, the Annus Mirabilis, which means the miracle year for those who don't speak Latin. But it's considered the miracle year because Einstein wrote 4 epic papers in physics while he was working in his patent office in Switzerland. And he wrote these 4 papers in physics journals that really kind of changed fundamentally how we think about physics. And he brought with him special relativity, and there's another one on Brownian motion and electrodynamics, all this crazy stuff. However, the paper we're going to discuss today, we're going to do a deep, juicy dive into one of his epic papers. This juicy dive is going to be on his 4th paper that he contributed to this physics journal. The title of this paper that our Mr. Albert Einstein had here is called, "Does the inertia of a body depend upon its energy content?" Quite the catchy title. What does this mean anyway? Does anybody have any idea what he's talking about here? I don't know what he's talking about. Well, sort of, kind of. Really what Einstein is getting at in this paper, which is crazy because this paper is actually only 3 pages in length. Just amazing that it's like a foundational paper in physics, and it took him 3 pages to do it. And I actually read through it, and it's pretty good. It's kind of confusing to me. He does use some super fancy math, but we're going to break it down here on a very simple analogy and a simple kind of visual to kind of help you guys, help myself to understand what he was discussing here in this paper as best we can. Hopefully we can, when we dive into this idea, we can suck up some of his super genius juices and maybe we can become a new kind of general relativity. Maybe. Maybe not. I don't know. Anyway, crazy that he only took 3 pages to really develop this idea, and this really took off from his 3rd paper, which is really more about special relativity, and this one is more about the combination of energy and mass being equivalent to each other. Pretty crazy. Amazing. So, Einstein begins his epic paper here with a very simple thought experiment. He imagines an object at rest, and this object is just sitting there, and it shoots out or it emits 2 beams of light. So we're going to imagine the bat symbol, naturally, or the bat beacon symbol. That's how I like to think of it as. Because, I can't really draw the bat symbol here, but I don't know how to draw the bat symbol, to be honest with you. Whatever, it's fine. Anyway, another bat symbol over here. We can do a little bat symbol. Okay, so this is broadcasting the bat symbol here and here. I'll have a cool visual for us here. But anyway, he begins his paper with a cool thought experiment. He's like, okay, I'm gonna have this object at rest, and it's shooting out 2 beams of light. In this case, it's broadcasting a signal to Batman over here, and broadcasting a signal to Batman over here. We have 2 beams of light going this way and that way. So in our case, we have an object at rest, which is our bat beacon, and it's shooting out beams of light. Now, using the principles of relativity, which he kind of first formulated in his previous paper, and also, has been around for a long time in science, but he kind of used relativity from his 3rd paper, those big ideas, to understand that would the energy content of these 2 beams of light, would they be the same for different observers? That's kind of what he's asking here when he talks about inertia and energy. So, in the first case, he's thinking of energy conservation and relativity. We're going to take an observer who's at rest. We're going to say this guy over here, he's just chilling over a stick figure here, and he's looking, he's like, wow, that's cool. He's looking over here, he's looking over there. Now, if this guy, in comparison to this bat beacon over here, if he is just at rest and standing there all alone and just chilling, he's watching, let's say it's Commissioner Gordon over here, so we got Commissioner over here just resting, looking for Batman, and like, what's the fastest way I can get Batman over here to help me out, to go get Capture Bane or whatever. Anyway, Commissioner Gordon is looking at this bat symbol. He would actually see, because he's at rest and he's not moving, Einstein recognized that his relative perspective, because he's at rest, these beams of light would actually be shot out, and not only would they move at the same speed, because remember, speed of light moves at the same speed for everything, so the speed of light is always a constant, it can't go above a certain amount. So not only would that be the same, its energy content would look exactly the same, and its momentum would look the same. So from this observer, the beams of light would go out at the same speed, like that, and they would also have the same energy content, like their frequency would be the same. So he could not see any difference between the energy content. And both of these beams of light would be balanced out. Basically the same amount of energy would be over here, the same amount of energy would be over here, bing, bang, boom, everything balances out, nothing fishy, nothing weird. Because this guy, our Commissioner Gordon, is just standing there chilling, watching these beams of light. Nothing really too crazy is going on from his perspective. However, if we change perspectives to someone who is moving, check this out. So, we're gonna imagine, I'll have a cool visual for you guys, but we're gonna imagine an observer who now is moving. So remember, this is all about relativity. This is all about different observers and different motions. This is what the inertia that he's talking about. So we're gonna imagine a little like hover car thing or something, I don't know. We'll have like Einstein in a hover car or something, I don't know. He's chilling, he's moving in his hover car. So, we have Einstein in a hover car, not the best drawing in the world, but that's okay. So anyway, this guy's moving in his cool hover car, his hovercraft, he's like, he's zipping by. Now what's interesting about this, Einstein recognized, like, wait a second, if this guy's moving, he had already talked about this in his special relativity, that events are not simultaneous. So in the case of this, if Commissioner Gordon's over here seeing these beams of light go at the same time, this guy would see events happen a little differently. So this beam of light, because it's going out towards him, it would actually be moving at a much higher frequency. So this would be moving at a much higher frequency towards him. And therefore, this beam of light, because it's moving towards him and he's moving right towards it at a faster speed than this guy, the energy content of this light beam would actually be more. The frequency is going to increase because as he's looking at it, it's moving towards him, but he's also moving towards it, so its frequency is going to increase. And there's going to be lots more little tiny wavelengths, which means the energy and the frequency is going to increase. Pretty crazy. That also means that this beam of light is actually moving away from this guy. So this guy would actually see the energy content be like this, and the wavelengths would grow larger, and the frequency would also go much slower. It'd be a slower frequency. In that case, it'd be slower or a lower amount of energy. Crazy. So this beam of light would be redshifted. If we're talking about the Doppler effect, remember the Doppler effect, this would be redshifted over here, and this would be blue shifted over here. Because the blue has a higher energy content and it's moving towards him, more energy, higher frequency, shooting towards him. Red, just like the expansion of the universe, we know it's redshifted because it's moving away from us. So because everything is being redshifted over here, it's moving away from us, it's a lower energy content, it's moving away from our hover car, Einstein over here. And so he would actually see, this is just a crazy fact to think about. Now, the momentum and the speeds of these would still be the same. So the light speed, he would measure the speed of these light beams would still be the same, but the energy content would be different. Crazy. How did Einstein figure that out? I don't know. We're just going to suck up some of his genius juices here. He did some fancy math on the paper, which I suggest you guys go look at. But yeah, so the really important thing to remember is that this guy would not see any imbalance in the energies here. The energies would all look the same. The speed of the bat symbols, the light from the bat symbols would be exactly the same. But this guy would see an energy imbalance. He would see that this energy, and remember, nature does not like energy imbalances. So because the energy is more here, because the light is coming towards him and he's going towards it, and over here there's less energy, there's actually an imbalance. And so what Einstein deduced is, using his fancy math chops, he realized that the mass of this bat, the bat beacon itself, this mass would actually have to change. So because to balance out this equation, in this scenario with a moving relative observer, if he's moving towards, parallel to these two light beams, that this mass would actually change. And this would create a stable, energetic system here. So the energy going this way would be a lot more, and the energy would be less here, and that would be balanced out by this would have to lose some energy. Crazy. But he realized because there's an energy imbalance in the light and the photons, that this also must have its energy decreased, or its mass decreased. And because the energy here is imbalanced, and the decreased mass balances out. He realized in that moment that energy and mass must be closely related. So because there's an energy imbalance, mass is also taken away, and he knew then that mass and energy there must be some intrinsic properties that they're very closely related to each other. And there we have almost like a very similar thing to his equivalence principle from general relativity, from gravity and acceleration. So here we can see there was almost this beautiful balance, or this beautiful symmetry, equivalence between mass and energy that he lines out here in this beautiful thought experiment, in this super short, condensed 3-page paper. Pretty epic, pretty crazy there. And in fact, when he was designing this thought experiment, he actually did the math to it, and his first initial findings with the math behind this, he did not come up with E equals mc squared on this paper. A lot of people say he got mc squared on this paper, but mc squared in fact did not come from this paper directly. It came a little bit later. I think it was like a few years later. He actually derived it from this. So that's going to about do it for our Einstein 1905 paper, the 4th paper in his amazing physics journal that he delivered from his patent office all the way back in 1905 in Switzerland. Pretty epic, amazing. There's our boy General Relativity doing it again, shocking the world, and with his crazy hair and his crazy science. Thank you, Einstein, for delivering these amazing papers. I want to bring that to your attention so we can suck up some of the genius juices and maybe make our own amazing theories on the universe all around us and within us. See you next time.